Hello, my name is Aaron Groff. I'm working with Dr. Harris in the Department of Chemical and Biological Engineering, and today I'd like to talk about my project, the catalytic synthesis of ethyl acetate via oxidative self-coupling of ethanol. Let's start with some background. Paracetamol, also known as acetaminophen, is the active ingredient in Tylenol. It's commercially synthesized using acetic anhydride and 4-aminophenol. This synthesis is effective in industry, however, it does have one major drawback. Acetic anhydride can be derived primarily from fossil fuels. Obviously, we want to get away from this as much as possible, given that fossil fuels have a detrimental effect to the environment. So I'm suggesting in this proposed reaction pathway that we replace ethanol with acetic anhydride in this synthesis. Ethanol is derived from biomass, such as corn and sugarcane, and thus it has a lot of environmental benefits. Also, it is cheaper than acetic anhydride, so there are also economic benefits for this ethanol-based synthesis route. However, this reaction is not viable under standard conditions. Ethanol and oxygen will not readily react to form acetaldehyde at typical temperatures and pressures. Commonly, to try and up the reactivity, we'll try to elevate the temperature. But if we go too high in this reaction, the dominant chemical reaction will be the combustion of ethanol, where ethanol and oxygen will react to form carbon dioxide and water. These products are not very valuable, and we want to avoid doing this reaction as much as possible. So we want to increase the reactivity without using the extreme temperatures that would lead to combustion. We will do this by using a catalyst. Catalysts are used to speed up some chemical reactions, and often it allows reactions to be industrially viable, which they otherwise wouldn't be able to be. They participate in the reaction, but they are not used up. You can reuse the catalyst for multiple series of reactions. Molecules will adsorb to the catalyst, and then this will make them more reactive. Catalysts can also promote reactivity at lower temperatures than normally required. They work by lowering the activation energy, which essentially just means less energetic molecules at lower temperatures will still be able to react. On the screen, you can see the three basic steps of the catalytic process. First, the adsorption, where a temporary bond between species A and the catalyst is formed. Then the reaction, where A and B react to form C, still with that temporary bond. And then the desorption, where that bond breaks and you form your product C, and your catalyst returns to its original state. Now, let's discuss how we'll evaluate this reaction. The complexity of the full reaction with ethanol, oxygen, the catalyst, and 4-aminophenol makes analysis a little bit difficult. We're not entirely sure what products will form, so we want to simplify the reaction, and we'll begin with just the first step of ethanol and oxygen, as well as our catalyst, to form acetaldehyde, the key intermediate. We want to form acetaldehyde, and it's hard to analyze the acetaldehyde concentrations because it is so volatile. Acetaldehyde will evaporate readily at room temperature. So instead of measuring acetaldehyde concentrations, we will measure the subsequent products of further coupling with ethanol, which would be the ethyl acetate concentration. In this scheme, ethanol will react with adsorbed oxygen atoms to form acetaldehyde and then subsequently react with another molecule of ethanol to form the ethyl acetate. Now, the catalyst that we'll use in this reaction is made by strong electrostatic adsorption, or SEA, and the goal of this synthesis is to create small and well-dispersed metal nanoparticles. This will increase the catalytic activity and give us the most product that we can possibly get out of our catalyst. So, how do we make these catalysts? The first step is picking the metals that we'll use, and we chose a palladium on silica catalyst because it has shown promise in low temperature oxidations of alcohols. We first create our mixture, and with water being our solvent, as well as the palladium chloride salt being our source of palladium, and Si0 gel as our source of silica. We then stir, and in the process of stirring, the palladium and chlorine will separate, and then palladium particles will adhere to the Si0 gel surface, creating our catalyst. We will then check the pH and adjust the pH for ammonium hydroxide, and our target pH is 10.5, and the ammonium hydroxide will bring this up, and we want the pH to be 10.5 because that will give us the best properties for the synthesis. We then will wash and cover the sample, and this will remove any of the impurities that were in there. We also want to vacuum dry to remove any of the water that still remain, reduce in the tube furnace to help stabilize the catalyst as well as prepare it for the reaction, and then we will crush and sieve the catalyst to get it to the desired particle size. The last thing for understanding our data is understanding how the reactions were run. We filled reactors with 4 milliliters of ethanol, 10 milligrams of palladium catalyst, and a stir bar. We then pressurized the reactors to 60 psi gauge of air, heated to the desired temperature that we wanted, and then we also allowed to react for the desired time. That 60 psi air is where our oxygen comes into the reaction. After the reaction, product solutions will be evaluated and measured to determine the identity and the quantity of the products that we formed. And another key critical part of this reaction is that oxygen is the limiting reactant in this process. There's only a certain amount of oxygen that you can fit in the headspace of this sealed reactor, and the maximum concentration of ethyl acetate when all of that oxygen reacts is 6.55 times 10 to the negative second moles per liter. So, as you can see in this chart, at 75 degrees Celsius reaction temperature and at 3 different times, 20 minutes, 40 minutes, and 60 minutes, you can see on the y-axis that our concentrations aren't really approaching that 6.55 times 10 to the negative 2 mark. We're down in the 10 to the negative 4 range, which suggests our yield is very low. Over these time intervals, we would expect the concentrations to be increasing, and also you can see that the error bars are very large here, but both of those things are due to our inability to accurately analyze these concentrations because there is so little ethyl acetate. Our next step was trying to up the reaction temperature. We tried at 120, 150, and 175. We didn't want to go too high. Again, we want to avoid that combustion reaction, but as you can see, elevating the temperature a little bit was able to produce a little bit more ethyl acetate, but still we're barely in that 10 to the negative 3 range as far as concentration, and that's just not enough to make this reaction industrially viable. However, in addition to ethyl acetate, we were also forming diethoxyethane, which we did not expect. Diethoxyethane is shown in yellow on this plot, and as you can see, there's a lot more concentration of that. In fact, that's approaching that 10 to the negative 2 mark that we wanted to see if we were going to deem this reaction having potential for industry. But we do not know how diethoxyethane is forming. So we took a quick look at what could be happening, and we found that the first step in the diethoxyethane formation scheme is actually the same as the first step in the ethyl acetate formation scheme, ethanol reacting with oxygen to form acetaldehyde. And if you remember, the whole goal of this simplified reaction was to see if we could synthesize acetaldehyde. That was the main goal. It was just measuring the ethyl acetate and the diethoxyethane were just auxiliary ways to determine if we could do that. So the fact that we're getting diethoxyethane formation and in the quantity that we're getting it suggests that ethanol is readily being oxidized to acetaldehyde in the system, and it's a very positive outcome of these experiments. So, in conclusion, the measured ethyl acetate concentrations were very low, much lower than we expected, but we were able to form diethoxyethane, and this was actually dominant at the higher temperatures that we tested. The presence of diethoxyethane thus suggests acetaldehyde is being formed. As for some next steps, I want to finish preparation of another catalyst, this one being palladium on gold, and the purpose of this is to compare it with the pure palladium sample, and gold has been compared in the literature to show some differences with the pure palladium, and we want to evaluate what sort of results that we get in these different reactions. Lastly, we want to introduce 4-aminophenol to measure the product production and evaluate product preference, and eventually synthesize that paracetamol, which is the end goal of what we're trying to do with this general project. With that being said, I'd be happy to take any questions from the audience now. Thank you.
You mentioned that a big part of what you're working on is economics and is making this process cheaper, but I believe that gold and palladium are both relatively expensive metals. How do you combat that in the economics of this project?
Yes, so that's 100% accurate. Gold and palladium are very expensive metals, but the key to understanding the catalyst is that they are reusable. So when you make these gold and palladium catalysts, you'll be able to run many and many reactions under these, and you won't have to buy them every time you would have to buy new reactants like ethanol. So the price difference between the ethanol and the acetic anhydride ends up being a much bigger deal as far as the large industrial scales that you'll be running this reaction at if the pathway is deemed viable. So that's the reason why it's more economic and in addition to the environmental benefits.
Can you go back to slide 9, please?
Yes.
Yeah, so it says there that you're setting the pH to 10.5. That seems like a pretty arbitrary number. Why is that?
So 10.5, actually, it comes back to what I was talking about with the palladium adhering to the zero gel surface. We want that pH actually maximizes this attraction. I mentioned how this is called strong electrostatic adsorption. That basically means that we're taking advantage of electrostatic attractions to bring the palladium to the zero gel surface. And 10.5 has been proven in the literature to maximize these interactions and maximize that in terms of getting our catalyst to perform as best as possible. So that's why we use 10.5.
As you analyze the data from the catalyst with gold, what differences do you anticipate?
Okay, so the palladium gold catalyst, we actually wouldn't anticipate too many differences with the basic reaction that I spent most of this presentation talking about. But more of those differences come in with gold when you start talking about selectivity. You can see on the screen that there's a couple molecules here that we expect we might be forming, and the goal is to form paracetamol, but we're not entirely sure how these catalysts will behave, and we want to compare the pure palladium to what the palladium gold actually synthesizes, and we expect there could be some differences there due to gold's tendency to have some different selectivity outcomes. So that's what we want to see with the palladium gold and evaluate the differences there.